Hi, this is ET370 lecture 15, 15 part A actually. And this is going to be a two-part lecture. In the first part, we're going to introduce this concept called SR flip-flops or set and reset. We'll look at how an SR flip-flop is used to store 1 bit of memory. This is how your computer, we can implement a way to store that. We'll look at an example sequence and how it could actually be used as a debounce circuit. In the next part, in 15 part B, we'll look at a clocked SR flip-flop, a data flip-flop with a latch, and a data flip-flop with preset and clear. But let's just look at this. And so I wanted to start off with this example. And I know this looks a little bit crazy, but this blue box here is where we have the set reset flip-flop. Okay, and so you can see the flip-flop nature because of this kind of cross connection. Notice it's built with two NOR gates. Okay, and we have the set and reset, and we have our output Q and Q bar. Remember, Q bar just means it's the opposite of Q. Okay, so let's see how this is attached to a circuit. Basically, I have two switches here. If I push the switch, set goes high. If I release it, set goes low to the pull down. If I push the switch 2, the reset goes high. If I release it, the reset goes low. Again, do the pull down. And then I just have Q driving an LED, and so I have a little NPN transistor set up, and it drives the LED. Okay, so this could be a physical implementation of where I just want to see this Q turn on and turn off, even though I press the set and release it or the reset and release it. Okay, so why don't we go to a simulation and just see the behavior. I want to have the behavior in your mind first before we go into the nitty-gritty details, because if you don't have the intuition, it's just easy to get lost. So let me go to that. So I'm going to look at this nice Falstad simulation of a 1-bit memory, and I'll have a link to this in the description. So you can see here, I'm turning on the simulation. Right now, we're at an arbitrary output. Happens to be keys. Notice if I reset what do you call it? The output is just random. But really what I want you to pay attention to is this. If I hit the set and I hold and release, the Q stays high. Okay. If I hold the reset, press and release, the Q goes low. And you can see that, right? So I hope you can see that this is kind of a memory in action, right? Notice the Q is like the memory. It's 1 bit that toggles high or low, and it stays there. It doesn't go away. So if I had a square wave coming into the set and you go bink, right? A little square wave, it's going to set this bit of memory high, right? If I have a square wave coming into the reset, bink, it's going to drop that Q low, right? And so I hope you can see that the LED or the Q is going high and then it's going low. Very simple action, right? And what I want to do now is go back and just kind of parse out and figure out how is this working, right? Because there's this interconnection. It seems simple, but it's a little tricky to get. And I hope after this lecture you'll understand how it's doing this kind of interesting behavior, all right? Okay, so let me stop this and let's go back to the doc cam. All right, so now that you have the intuition, let's just walk through the pieces and talk about some of the applications. Like one big one, 1-bit memory. I hope you can see this Q goes high and low. We'll see at the end of this short lecture the application of a debounce circuit. And then these are the 3 things we'll see in the next lecture, but we'll look at how it's used as shift registers, right? At frequency dividers and how it can be used to send data. But the flip-flop is very fundamental to a lot of our modern day electronics. All right. So again, there's 2 inputs, set and reset, and we have 2 outputs, Q and Q bar. And just a reminder, the bar means not or inverse. Okay, and typically, if you were to just kind of put this in a box, you could see 2 inputs, 2 outputs, and we know it uses NOR gates. Okay, so these are NOR, and let's remind ourselves what a NOR gate is. Okay, so a NOR gate is something like this, and here's my truth table for 2 binary inputs, 0, 0, 0, 1, 1, 0, 1, 1. And for an OR gate, A plus B, that's pretty easy, 0, 1, 1, 1. So a NOR gate is just the inverse, 1, 0, 0, 0. But I really want you to have this main takeaway. For a NOR gate, it's only true when both inputs are false. Otherwise, if any one of these are true, we have a false on the output. That is key for this understanding. So I'll repeat it again. It's only true when both inputs are false. That's going to really help our understanding of this flip-flop. Okay, so what does the truth table look like for this overall SR flip-flop then? Well, I'm going to give you this, and we will see why this is true through example. So if I take these two inputs, right? So these two inputs, A and B, are the two inputs that would go to the NOR gates. R and S are the two inputs that goes to the SR flip-flop. Don't get those confused. So I'll say that again. R and S are going to be the inputs to the flip-flop itself, right here and here. Whereas A and B, in this case, would be the two inputs going into the NOR gate. So in this case, it would be Q bar and R. And in this bottom one, it would be Q and S. Okay? All right. So the truth table for the overall flip-flop is going to be this. We haven't proven this to ourselves, but I just want to write it out. If I hit the set button, notice Q goes high. That matches our behavior here. If I hit the reset button, notice Q goes low. That's right here, that the LED turned off. If I release the set or reset, it goes to this Qn-1 or Q bar n-1. You're like, what is n-1? Well, if n is the current state, n-1 is the previous state. Kind of like in the lab, we talked about button state and button state previous. Well, this is previous state here, okay? So if you have 0, 0 on the inputs here, the output is whatever it was previously. If I hit set, the output goes high. When I say the output, I mean Q, right? And when I hit reset, the output goes low. And the Q bar is just the opposite. Now, we'll also show that 1, 1 is not allowed. It's not a desirable state. So we really try to avoid doing 1 and 1, and for the reasons of unpredictability, and it erases the memory, okay? All right, so let's look at an example sequence of an SR flip-flop and just build the fact that this truth table is true. Okay, so let's say we go through a sequence where we press and release the set button. So what do we expect? If we press and release the set button, we should be bouncing between these two states. So if I press set, I should see Q go 1, and if I release it, I should just see it stay 1 and 0. Okay, so let's say we're here. So I'm at 0, 0, okay, 0, 0. I'm at some random output. I don't know what it is, 1, 0, 0, 1, whatever. Okay, so now let's say I'm gonna press and hold the set. Let's see what happens. This is probably the most complicated part of this whole SR flip-flop. All right, so I have the flip-flop here. If I press set, which is this one here, and this is some random, we know from the NOR table, right, what happens. Anytime we have a 1, you're guaranteed to be 0. You must be 0 here on the NOR. Okay, that's fine. Does it mess anything else up here? Let's see what happens. So we have a 0 here, and that's cross-connected to this input on the top. And so what do we have? 0, 0. Oh, we now know that this has to be 1. Fantastic. Okay, and so this is great because Q and Q bar are 1 and 0 respectively. Okay, now does this 1 go down here and mess anything up? Do we get like some unstable behavior where this turns 1 and then this goes 1 and this goes high and low and it kind of chatters back and forth? Well, let's see. So I have 1 here, this made a 0, right? This 0 guaranteed that this was a 1. Okay, so now we go back 1 and 1. 1 and 1 for this NOR input. 1 and 1 makes 0. Yay, this is good. This stays 0 and we are stable. That's a good thing. So notice there was like kind of 3 complicated steps. The second I pulled, the instant I pushed S, right? Now let's say I'm holding S, and then I release S. What happens? As I release S, this is gonna go to 0. And so now I have the 1 here, 1 and 0 still makes 0. That's good. 1 and 0 still make 0. And then look at this. This 0 propagates still back up here. 0 and 0 still make 1. And so now that memory effect is taking place where we're here at the Qn-1, Q bar n-1. So we just bounced between these two tables right here. And notice the NOR helped us build this intuition. Okay, let's do the same thing for the reset. So I'm going to push this to a side. Okay, so for the reset, what we're hoping for is to bounce between these two rows, right? So we have Q equals 0, Q equals 1. Yeah, Q bar equals 1. But let's again start from this part where we have some random output. Okay, some random output. And this time I'm going to hit the set button, the top one. So the set. So when I hit the set, this is 1. Okay. So what happens when I have a 1 for a NOR? The output has to be 0. If there's ever a 1, the output has to be 0. Good. So then this 0 propagates down and I have a 0, 0 here. What does that mean? That means that this output on the bottom has to be 1. Okay, good, do the NOR. And this is good because I get a 0, 1. I get what I expect, 0 and 1. Okay, and then what? Once I go here, I go, well, does this mess anything up? Do I get any unstable behavior? Well, let's check. 1 and 1 coming back up to the top. I think that's not going to be a problem. I'm going to stay 0. And so I have a stable condition here. So if I press and hold R, I get 0 and 1, 0 and 1. Now, if I release R, so I go back to 0 and 0, what happens? If I release R, this now becomes 0. Okay, then what? 0, 1 stays 0, good. And the 0, 0 on the bottom stays 1. Excellent. So again, the memory action is taking place. So I bounce between here, there, and back. Excellent. Okay, so that's the set and reset. But what about this not allowed state? What about this not allowed state? So I'm going to move this over. Okay, so one problem is, like we said, it erases memory, right? And it's unpredictable due to what we call a race condition, right? So let's see an example of that. What happens if I set both of these high, 1 and 1? Well, if I set both of these 1 and 1, the outputs of either one of these has to be 0 and 0 due to the NOR condition, right? Right? If I have a 1, it doesn't matter if this is 0 or 1, it's going to be 0, right? And this is going to be 0. So they're both going to be 0, all right? Okay, now let's say, for example, we wanted to go to R equals 0, S equals 0. So we wanted to jump from here to there. Okay, and so what would we expect? We want to see that we go from 1, 1, 0, 0 to 0, 0, 0, 0. That's what we would desire, right? We would expect a 0, 0, 0, 0. Now, the problem is if you're holding these two buttons, and even if you're electronics, right, it's very difficult to release them perfectly at the same time. Like to go in, from 0, 0 to 1, 1 or 1, 1 to 0, 0 perfectly. What happens is you'll release one a little bit faster than the other, right? And so let's just see what would happen. So let's say we start at 1, 1, 0, 0. What might happen is this. You might release the R a little faster, right? And so you'd have a very short time where you have 0, 1. Well, if you have 0, 1, what happens? Well, we know what happens. Q goes high, right? And then once you release 0, you're left at 1, 0. Okay. What if you had the other situation where you started at 1, 1, 0, 0, and you released the set a little bit faster? Well, the set a little faster, so you get 0, 1. So you get this condition. And then what? You release both finally, and you get 0, 1. Notice it all depended on how fast you're able to release. Both you're trying to do the same thing, going from 1, 1 to 0, 0. But in one case, you release the reset a little faster. Here, you reset let the set go a little faster. It's unpredictable. Okay, so this is why we don't want to live in this state, right? We just want to avoid it. So you just kind of want to stay there, right? So I hope this set reset idea is not too bad. Okay, the last application in this short first part I want to talk about is a debounce switch. Okay. And so let's say you had a button here. So you have an Arduino or microcontroller, you have your pull down resistor button. Let's just recall how this works. I have 5 volts here. Right now, this pin, this voltage sees 0 volts because it's being pulled down by this resistor. I push the button, what happens? This signal is now sent up to high voltage and this 10K supports it. Okay, so this is fine, but what if there's chatter? Because what happens, sometimes there's mechanical chatter. You press the button and you see something like this. Bink, 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 and then it goes high. So this is bad because if you have, let's say, a circuit that's trying to count the number of times you've pushed a button, this might count 1, 2, 3, 4 pulses, right? When you only wanted 1, okay? All right, so what would be a solution? Well, we can actually add an SR flip-flop, and let's see how that works. So what you could do is this. I could put a switch here, which starts at reset, and then switches over to set. And let's see what happens. I'm going to now set the input into the Arduino as the output Q. So I have a 5 volt signal. I can throw this, right? So that's my momentary button going between reset and set. And so let's see what happens. So if I'm starting at reset and I push to set, and even though there's bounce, so bounce isn't going away, but bounce exists, right? And so I push down bounce. What happens to Q? Well, remember, if I'm bouncing between 1 and 0, you can see that the output Q is always going to stay high unless I press the reset. So if I go here and it goes chatter, 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 right? What happens is you're going to get reset 1, 0, then you're going to go set 1, 0, 1, 0, 1, 1, whatever it is, bounce, bounce, bounce. But the Q is always going to have 1. This is no bounce. You've debounced your circuit electronically, no software, just a little chip here in the way and no problems, right? So this can make a much more robust, reliable system for your buttons. Okay, hope you learned something in this lecture, and I'll see you in the next part.